Hey guys, so we're going to be doing the final problem on the EE301 12-week review packet, which is concerning a high-pass filter. This is problem 19. So a high-pass filter, I don't know if you watched the video that we did before on problem 18, but a high-pass filter in the context of RC circuits, so resistor capacitive circuits, are going to be defined by having the load taken on the resistor. So a low-pass filter, the output is on the capacitor. A high pass filter, the output is on the resistor. So this is important to know, at least to refresh yourself before the exam, because you may find that they won't give you the name. You may have to determine that for yourself, and you don't want to be using the wrong set of equations. You don't want to mistake one circuit for the other. You'd probably still get some partial credit, but you want to avoid losing any points entirely. So let's start with the first part, which is our cutoff frequency. So the idea behind a high pass filter is that they only allow high frequencies, and how high the frequency is determined by the type of capacitor and resistor you use. So we look at the bottom of our AC equation sheet, and we see an equation that says FC is equal to 1 over 2 pi RC, and that is true for high pass filters and low pass filters. So that's going to be 1 over 2 pi 100 killi, and then that'll be 20 pico. Remember, pico is 10 to the negative 12, and that's going to get us roughly 79.58 kilohertz. Remember, frequency is in hertz, but usually if you have something high, you use a metric prefix like killi, mega, giga, whatever the case is. So the next part is going to be concerning the voltage gain. It's going to be demonstrating how the circuit works at both high and low frequencies. So right now we're going to take a low frequency. It says right here that we're going to be using about 1% of the cutoff frequency. So let's calculate that out real quick so that we don't have to worry about it. Frequency is equal to 0.01 of the cutoff. Cutoff was right here. So that's 0.01 times 79.58 killi. Which is going to give you roughly 79.6 hertz. So next step we're going to take is we're going to solve for the capacitive reactance. Okay, so that's just 1 over 2 pi FC. So 1 over 2 pi times 796, and then finally at 20 pico, pico being 10 to the negative 12, which is going to give us 9.997, almost 10 megahertz. Okay. Finally, we will plug in the value we need for this gain equation. So this is for a high pass circuit. Okay, so you're going to want to use that high pass side, which is the right side, and that's going to be 1 over square root of XC over R squared plus 1. We'll plug in the numbers. We'll get 1 over the square root of 9.997 mega over 100 kilo. Remember to add in those metric prefixes. They're important. So top would be times 10, 10 to the 9, my apologies, 10 to the 6th. And then the bottom would be 10 to the 3rd. Plus 1, and then that would get you roughly, calculate that out, 0.01, which they want you to compare it to the minimum level, which is 0. Obviously, this number is very, very small. So this is a very, very small gain, meaning that if you put a voltage in at that frequency, you would only get 1% of that voltage to the load. So if you put in 100 volts, the load would see 1 volt, which is pretty much nothing. Anything that would require a 100-volt input would basically not turn on at all, which is what you want at the low frequencies with a high pass filter. Now we'll see with this other section that it'll be the opposite effect. I'll zoom in a little bit so you can get some more room. So right now we're going to be doing 100 times the cutoff frequency. So frequency equals 100 times FC, which is going to be 76. Oh, my apologies. Our FC was 79. 79.54 or 58 kilohertz. And then that's times 100. And that's going to give us roughly 700 or 0.796 megahertz. All right, so that's a pretty high frequency, and we should see better results since this is a high pass filter. So we'll use the same steps. XC equals 1 over 2 pi FC. That's 1 over 2 pi 7.96 mega. And then the capacitor was at, if I'm not mistaken, 20 pico. And we'll just multiply all this together, and we should get roughly 999.72 ohms. Okay. Oh, my apologies. I believe I made a small mistake over here. Your X value should be in not hertz. That's silly. Ohms, mega ohms. The metric prefix is still the same, so the math should have worked out. But if any of you noticed that my units didn't quite work out, that was my mistake. My apologies. So anyway, this will be in ohms, which means no metric prefix needed. So all we have to do is plug it into our AV equation, which is 1 over the square root of XC over R squared plus 1. And that is all square rooted. You can use either the square root symbol or the 1/2 power symbol. It won't change anything. 1 over, let's see, we've got 999.72 over a resistor, which was, if I'm not mistaken, 100K squared plus 1. And that's all square rooted. And that's going to get you roughly 0.99995, which is basically 1. What that means is that you're going to get maximum, near maximum passing of the source voltage. So if I put in 100 volts, I'm going to be getting 99.995 volts to my load, which is almost the whole thing. And that's what we want. For a very high frequency, we want almost complete transfer of power to the load. And conversely, for a low frequency, we want basically none to the load. We don't want the load to turn on at all. And that's the point of the filter. For this problem, one last point, you may have seen, if you check the key, you may have seen something like AV equals R over square root of R squared plus XC squared. That is the same exact equation as the one we used. The only difference is that they multiplied by R on the top and bottom to get the numbers that they needed, but it is completely the same. You can use either. This one, the one I'm circling in red, is the one that's on your equation sheet. So this is the one that I'm going to use just to keep it simple, but you can use either version. It'll give you the same exact answer. Last part, determine the frequency at which the gain